morning for all of you. And today we receive here in the Centro de Informática da Universidade Federal de Pernambuco, Professor Boris Mirkin from the Higher School of Economics of Moscow. And I met him, I was very young. He was already a star in cluster analysis. And we used it to meet in the Conference of International Federation of Classification Societies. And then we thank you very much to spend your time and to visit us here in Recife. Please, you can start.
Thank you. Thank you for inviting me. And it's an honor to speak to this audience. This method is one of a few methods that I've developed and kind of still applying it and further developing. So it's a kind of mysterious to me. My talk will be in 4 installations. So the first goes introduction. Then I am talking about K-means method and its derivative, the anomalous clustering method. And then I present 3 applications. And here, last not least, is not shown, conclusion to my talk, quite short. So let me start from the concept of classification. The concept of classification does not belong in the sciences. It's amongst several concepts introduced by the ancient scientist Aristotle and thrown out when the science in 17th century with Galileo Galilei, Newton, and the others, they threw out most Aristotelian concepts, including the concept of classification, although classification is everyday use of every person. Here I'm going to show to you an example. Temper types was introduced by the ancient medical doctor Hippocrates. It's not named for me. It's a guy who can treat horses. So he developed this concept that there are 4 different juices: the blood, bile, lymph, and black bile. And depending on the how much each of the blood take in the body, there are 4 types that he called sanguine, choleric, phlegmatic, melancholic. They are quite useful. Recently, they were reanalyzed. So a Russian scientist, Nibelitin, came up with 2 features defining this typology. It's about the reaction, about the nervous reaction of humans, the speed, and the strength of the reaction. So depending on the prevalence of this or that, there are 4 types, and they correspond exactly to these types. Now, to be honest, the concept of typology is the least developed in sciences. Whatever we do is mostly concerns the hierarchical classifications. Although in practice, we also have typologies based on just one type. Like in politics, we have NATO, we have political parties. They are singular types and still working. So these are not quite well analyzed in mathematical theories. And this is what I'm going to present you, a kind of hierarchical, a kind of cluster in implementation of these typologies using just one type. So I'm giving you a common example, iris data table. It's 150 iris specimen divided into three types according to these pictures, and with four features. I think I'm not going to show anything about data tables, so I'm not going to discuss it right now. So I'm going to, so the task of clustering, where is clustering task? No? So I removed a very important slide. So clustering, not removed, it's here. So the clustering is empirical classification. Is empirical classification over a data table when no unique classification base is given to us. So this is where clustering applies. And I'm talking to you now about the most popular clustering method to imitate typology. So on the left, you can see the geometrical picture. The stars present these types represented by just centers of clusters, and every object or entity is assigned to its nearest center. They are represented by big black dots on my picture. So the criterion of the k-means is to minimize the sum of distances between objects and centers of their clusters. And the distance here, when it was, so the distance is just the squared Euclidean distance. It is shown on the bottom of this picture. K-means works, I'm not going to explain to you how it works. It finds all clusters and centers in parallel. And I want to reformulate this criterion so that I could obtain clusters one by one. And I first came to this back in 1987 as a method I called principal cluster analysis. It was in parallel with principal component analysis. At that time, principal component analysis was considered as not belonging to data science at all. In machine learning, it was considered just an auxiliary method. And I was insisting, well, who cares what a Russian could insist on? Still, so within this framework, I developed this method. Now I don't call it principal component cluster analysis. I call it anomalous cluster analysis. So this is all mathematics behind the method. So on top of you can see the criterion of k-means. And next line is just you take Newton's binomial, they open the squares, and then the next line, this one is just taking one by one, and there is a very small mathematical derivation to kind of merge together the last two items into this thing. So in the end, we come up to this decomposition that I call Pythagorean, because it is Pythagorean. So what we have here, the sum of squares of all the entries in data table. They call it data scatter. We have the criterion of the k-means that we want to minimize. The t, the data scatter is not is constant. So if we want to minimize this, we must maximize this. This is a complementary criterion that I call explained part of the data scatter, and what we minimize is the unexplained part. And this now I'm going to draw your attention to this additional criterion. I use this decomposition, the Pythagorean decompositions, for two applications. One, the second application is the analysis of categorical features, which produces quite beautiful results or better to say not elegant results. Here I'm using this for the other goal. So this is what we say, the complementary criterion. What its meaning? So this is the complementary criterion that is to be maximized when we minimize the k-means criterion. So what do we want to maximize? It's the sum of contributions of individual clusters. So it's an additive thing. Nk is the number of elements in cluster, and ck squared is the squared distance between 0 and the center. So this has quite simple geometric interpretation. What you want? You want to find clusters that are numerous, that nk must be big, and the distances to center also big. So this is what you want. This is why I call it anomalous and anomalous clusters. And if you put center, if you put the origin of the space in the center of your data, of the points in your data table, then this is indeed anomalous and populated cluster. That's what you must find. And indeed, in this decomposition, what is important to mention that the left part does not depend on the origin, and the right part does depend. So this was a very puzzling thing until I realized at last that basically this dependence is not quite important, because if you change this of the data set, you still have the same criterion plus constant. It does not depend on the partition. So this is my strategy then. If I would be more, how to say, more clever, I would say, I would proceed in parallel way, finding all clusters simultaneously. And I never attempted this, to be honest. So I leave it to my audience. If you wish, we can explore together, or you on your own, how this method should work. I'm going the approach A. I take clusters one by one. So I take first the most distant. I find it and remove it. I don't change the 0 because the 0 is on this picture. Then I remove the next one and so forth. The entire idea is quite clear. I just want to see my work. Okay. So this is how this method of finding an anomalous cluster works. So this is the criterion. I removed K. K is a label of cluster. I want to just to find one cluster, S. S is one cluster. The vertical lines denote that it is the number of elements in this set multiplied by the square distance from its center. So on the left picture, we have two pictures here. So the left picture shows this is the center, the origin. I call it reference point because it can be any. As I showed to you, that doesn't much depend on the position of the center. So whenever you fixed a specified reference point, the process starts from the most distant. You find such an object which is the most distant in terms of the Euclidean square distance. So this is the center of the cluster that you want to find. And now you do what k-means does with this specification. So you check every other object and you assign it to either this center or to this center, depending on the distance. So all these points go here, all these points go here. And then you recompute the center. The center is the mean, so you recompute it as the mean, and so forth. So you do these iterations, they converge, as k-means converges. So each iteration, you change the center of this. You never change the center of this. It's always 0. So you come up with this cluster, and you call it anomalous. You take it off, and you can continue. So this is, how to call it, pseudocode for this algorithm. And you then can continue one by one. So you first remove the most distant. I'm not sure that it is drawn correctly. So this is the most distant, you remove it first, then this, and so forth. You're removing them until no objects to cluster remain. This is how it works. With this, I introduced what I call intelligent k-means. Intelligent k-means works in this way. First, you find all anomalous clusters. Then you leave only the largest of them. Depending on various considerations, I still don't have any good algorithm to select the. If you have a k specified, you have the k largest clusters. Or you can have the minimum number of objects in a cluster. So such a threshold to fix. Then you take only those of your anomalous clusters that are larger than this threshold. And then you take centers of these largest clusters, the beginning as the initialization of k-means. And you run k-means after this. This is how this intelligent k-means works. So now I'm going to show you, and this idea was applied at various data sets, not necessarily like this. It can be similarity data, or I'll show you a couple of other data. So this, I'm going to present to you 3 applications. How this anomalous idea goes for generalization over a domain taxonomy. We had 2 applications of this. I show only one. Then the upwelling. There is a phenomenon I'll tell you later. And now the interval features that we do together with Professor Carvalho. So it's an analysis of tendencies in data science. This is the application. Analysis of tendencies in data science according to publications. So in 2018, we took a taxonomy of data science. We developed ourselves based on the taxonomy by the Association for Computing Machinery, this 2012. This is our base. I don't risk create entirely personal taxonomies. I don't feel myself that big. So I take the base, this ACM, Association for Computing Machinery, it's a worldwide organization. They created first this taxonomy in 1998. They created the next one in 2012. So I'm expecting the next to be creating is in 2026. So next year, I expect a new taxonomy reflecting the developments. So here we take this taxonomy 2012. We take 17 data science journals by Springer. Springer gave us open access. Now Springer gives open access to anybody. At that time, we had a special relation because the deputy chief of Springer was a Belarusian person, Alexander Biryukov, or in Belarusian, Biryukov. So this is why we got this permission. So we downloaded 17,000 research papers. We could not read them, too long, so we took only abstracts. And also this taxonomy that we had, it had 317 leaves, the concepts in the end, the granular concepts. So we computed that big matrix of relevance based on my previous developments, started from London. We had a paper published in the journal Machine Learning on this, and we further developed it in Moscow. It's called AST, Annotated Suffix Tree Method. So there is a concept of suffix tree. It's a good presentation of text in computer. And these suffix trees we annotated with symbols. And then we applied this method using the conditional probability of the last symbol in the sequence to maximize. And I'm happy to learn that the current LLM models also use this very criterion for their development. After we found this relevance matrix, we also aggregated it to a square matrix between the leaf concepts and applied again an anomalous clustering method we call FUDDIS. Fuzzy, additive, spectral, something like this. It is published in the Information Sciences Journal. I have it here. Yeah, it's the first paper mentioned here. This ADIS. And with these anomalous clusters, we analyzed rather successfully. I'm going to show you one of the clusters that we obtained. So these are membership. It's a retrieval, information retrieval. These are the leaves of the tree that belong to this cluster. And then we had our own method for lifting, optimal lifting of this. So for information retrieval, we got two head subjects. Information systems and the computer vision was not trivial at the time. So we decided that probably it shows us the tendencies that the visual information should be structured in a way like words in a language, leading potentially to word net of images. I think it's for the next 50 years. So this paper was published because nobody could obtain such a result. Several research groups analyzed the publications, but their conclusions were less interesting, I would say. Another application, it's a Portugal, purely Portugal. Maybe in Brazil it's similar, I don't know. There is an oceanic phenomenon which is called upwelling near the. So the white here, it's both pictures represent Portugal. White is the Portugal coast, and this is the ocean. is the temperature. SST, what they call it, sea surface temperature. Red is very hot, blue is very cold. So these are the colors. And an oceanographer tells us, oh, here is the upwelling. What is upwelling? Upwelling, as they suggest, is a phenomenon that there is a wave standing in the length is about 100 kilometers. The radius is about 5 to 10 meters, and it is rotates like a tube, bringing fresh water down 10 meters deeper, and the water from 10 meters deep to the surface. Fish loves this. So there are plenty of fish when you have this phenomenon, which is very important for the Portugal economy. Probably, I never heard of any research near your shores, but in Baltics, so they observe similar phenomena in many other offshore zones. So unfortunately, nothing is known on the modeling. They don't know how it is formulated. The only way to analyze is an oceanographer takes a pen, takes this map, and draws a very complex line. Oh, this is the upwelling. With our anomalous clustering algorithm, which works on pixels, you take the most cold pixel and do these operations as I showed to you, the anomalous cluster, and it comes with this green drawing, which in 90% of cases completely coincide with what the oceanographers draw. And so we could apply this method to 3 shores, one in Portugal and 2 in Morocco, the North Morocco and the South Morocco. It's Mediterranean and Atlantic. And we found out in all of them, with our analysis, that this upwelling is more or less constant. It changes 3 or 4 times, 3 to 5 times a year. And we could find these moments. And we are now waiting for a mathematician to kind of, or physicists to explain how it works. We are currently engaged with the winds. The oceanographers say that this relates to the winds, so we analyze now our stability periods in the relation to the winds, and it is still ongoing work. Last not least, I here show in a solid font Francisco Carvalho, whose visit to our university 2 years ago initiated this work. It's about clustering of interval values data. It's his data. Well, not his, he showed us. So you have these mushrooms. In the sciences, they are called fungi. I have time. They are referred to as fungi, fungi in Brazilian, I guess. And you can measure the most obvious items, the diameter of pileus and the length of stipe. So when you have an individual specimen of mushroom, you can say the pileus is 80. But when you take a category of mushrooms, like this I cannot pronounce, Mycena californiensis pileus. It's Roman. So it's in an interval because there are different specimens and they run between 70 and 200. So Francisco indicated as website at which information of 560 species of fungi in California are described. Unfortunately, the features that's shown are not exactly of the format that we could pick up. So we picked only 188. Still, it's much more than anybody else did. So we have now a table with 188 rows of these categories of fungi. And these are the features and the intervals. So we extended this method of anomalous clustering to this data. And also we took, also based on advice by Francisco, the Brazilian scientific production database. It appears that every team in this country is represented by 33-dimensional vector that described how many times they did one of these 33, how many times they produced each of these 33 items, like conference abstract, number 8, or a paper in International Journal, number 2, or just a paper, number 3, or artwork. You draw a caricature, and it is counted. I don't know how, it's a joke, of course. I don't know how it is counted, but this we could assess. We got the data table of 5,000. So in this country, we have 5,600 of research teams characterized in this 33-dimensional space. And we aggregated this into a much smaller data table. Instead of individual teams, we picked different various subfields of the sciences, 76 altogether. Here I present 5 of them, areas. And these are these 33 features. We also aggregated into just 6 types of output, of research output. Whatever did not fit into the first 5, the first 4 we called others. And we applied this method. Unlike the other k-means, that you don't know what are the initial clusters, you run it 100 times. And the anomalous clusters, you run only once. And they show quite a good cluster recovery, not optimal, but always within 25% of the optimal. And here my conclusion. If there are questions, I would be happy to answer. Can see none. My conclusion is this, that the anomalous cluster criterion is an offspring of K-means clustering criterion due to this Pythagorean decomposition and its one-by-one application. And they are quite worth to apply when no prior information of the number of sizes of clusters is available. All the examples that I showed were based on these anomalous clusters. And there is an issue that kind of haunts me. What are the cluster structures for which this method is adequate? How can I describe mathematically cluster structures for which this method is adequate, because I know that it is not adequate when clusters contribute equally. This method picks up the largest contribution, then the next largest, like a planetary system. My view is that these natural systems that are organized like planetary, so we have Jupiter with the mass greater than all of the together, then you have Saturn, and so you can find 3 or 4 planets with this method of mine, and all the rest, these smaller planets, remain like singletons, like Earth or Mars, for this method. And I'm yet to find the cluster structures at which this method is adequate. Thank you very much.
Someone would like to make a comment or a question?
Good morning. Thank you very much for your talk. Can you hear me? Can you hear me? Sorry. Can you hear me? Yes. Oh, yeah.
If you speak a little bit louder, it would be easier for me.
Okay. Good morning, and thank you for your talk. My question is, I'm out from the field, so I'm trying to get an intuition of what do you gain with this initialization. As you said, you can use your method as an initialization or a different way to compute the clusters. Would it have any guarantees like k-means plus or for being closer to the optimal value of the final criterion? That would be a first question. Is there any comment on this?
If I understand, I'm sorry. If I understand your question correctly, the question is this: when you find the anomalous cluster, is it optimal in the sense of criterion or not necessarily? Is it your question?
Yeah.
No, it is not optimal. Even with this example of iris, my first cluster, anomalous cluster, is 60 specimen out of 150. Next is 50. So 60, then 50. And this 50 contributes more than the first 60. So this shows that it is not optimal. It is like k-means, it is just a method alternating minimization. And it does not necessarily converge to the optimal solution.
Mhm.
It gives you a local optimum.
Okay.
So even here, there are some ways. I'm not even sure the problem of anomalous cluster, is it exponential or it is polynomial? I don't know. No. So it's an issue for the exploration.
And so as you mentioned, can you apply this idea for different, or have you seen or have you tried this in different alternating optimization approaches for clustering? I mean, with data, I mean, you applied for interval data, for point data, but I mean, I have any specific application in mind that I can think about, maybe I can mention later, but I've done in the past something like for trajectories, where trajectories are my points, like lines are my points, and then the centers are of a different nature, are not the same nature as points. Like I represent them as a different nature. I was wondering if I could apply them with some of these ideas. So the concrete question is, can you apply, or have you tried, or have you seen applications with different alternating optimizations?
Well, I applied it only to real data sets, about 7 or 8 times. Here I showed 3 of these applications. And each time it was quite successful. My clusters have been interpreted as a kind of natural and so forth. And I can add nothing.
Okay, thank you.
So there is no further investigation. We did investigate. I had a data generator, artificial data generator. I had a PhD student from Taiwan. We published a paper in 2010 in the Journal of Classification. Quite extensive experimentation of various approaches to determine the number of clusters. And this approach also was tested, and it did not come as a record. It was not the best in terms of finding the number of clusters in our experimentation. It was too long ago, I don't remember much. But this paper is available on web. So it's my name, Boris Milkin, Journal of Classification. I published maybe 5 papers there, so it should be among them. And my second co-author was Chinese. His name at that time was Mark Chiang, C-H-I and Chiang. Asked him, is it the same as Chiang Kai-shi? He said, yes.
Okay, I have a question. Well, I think that I understood finally why you call this anomalous, because you have the reference and then which is fixed, the reference point, and then you start with the fastest point, and from this point you got the anomalous clusters that you. This is the idea, I think. So is regarding the reference points.
Yeah.
So all the other are classified around the reference point, and there are some the anomalous cluster that is the first one. Okay, this is understood. But my question is that you have developed this decomposition from k-means, from the criterion of k-means. But you have applied also in fuzzy. And in fuzzy, there is this decomposition, but it is dependent of the membership degree. How, for example, in the other papers, you use this approach, but in the framework of fuzzy.
To be honest, I never tried.
No,
it's a quite relevant question.
Yeah.
I have this model.
Yeah.
We applied it a couple of times. The last time with Susana Nascimento from Portugal. It never occurred to me that I could try this decomposition.
Okay.
Thank you very much for your question. I will take a look at it.
Okay. Well, there is other comments. And
Thank you, Professor, for your talk. Have you developed methods to take into account the influence of the features for the clusters?
Take into account
the influence, the importance of the features for the clusters.
I did. I had a Brazilian PhD student, Renato Amorim. He defended when I was in London. He defended his thesis in 2011, and we published a paper, something like Amorim and Mirkin, weighted k-means, weighted Minkowski k-means. And it was quite successful. For this iris, the conventional clustering gives 17 errors, 16 to 18 errors. So you cluster them in 3 clusters. You want to find the taxa that I showed to you, these 3 taxa, and it's okay. It gives you more or less up to 17 errors. With this weighting of features, quite useful. We did not invent this. We picked up some Chinese idea, but the Minkowski we applied ourselves. So instead of a square Euclidean, we used the P, the power was P, and we changed it when they described how to find the good P, the power, and we made 5 mistakes only. The best machine learning methods, supervised machine learning, give 5 mistakes. With our unsupervised method, we also obtained 5 mistakes. It's a record in my view. So Renato Amorim, who is now unfortunately not in Brazil, I advise him to go to Brazil. He is in the United Kingdom.
I think that the question is also that if you could take into account the weight,
The weight of a
in
feature.
anomalous clustering.
We tried with our paper. We did it. Unfortunately, I don't remember results. This paper now is in a journal under revision. I cannot remember. We used the weighting system, the same weighting system. I cannot remember results, unfortunately.
Okay.
So
Well,
he knows. There is a manuscript. He has it. So it is described somewhere. I don't remember that it was much important with those two data sets that I showed to you.
well, any other questions or comments? Yeah, please.
One thing that got me in the beginning of your presentation, you mentioned that your method was once called principal cluster analysis, right? In the beginning. So I was just wondering, is there any kind of connection with principal component analysis, or is just the name that's similar? There is any relationship that we can?
Well, there is a relationship. They both are special cases of matrix factorization model. If you have anything I can write.
I do have.
There are. Okay. I'm sorry to bother. There is. So if I write here, is it okay? Or it should be better there? I think better here. So you have a data matrix, and you decompose it into a product of simpler matrices. This is called up to, of course, up to some residuals. This approach is referred to as the matrix factorization, and at least 500 of 24 it's too much. 500. I said 500 is too much. No, 24 different models fall within this framework, including principal component analysis. So you have this matrix. It is of the size of, say, this is the number of objects, and this is the number of features. And you decompose it into a matrix of n by k. K is the number of principal components, and k by v. So this matrix is of factor scores, and this is of the loadings. Yeah. Its rows are loadings of this matrix. Usually they denote C transpose, but in this context, I don't want the transpose. So this rows of it are the loadings, feature loadings corresponding to individual Y's. And the only thing that I'm a bit, stealing here, cheating on you here, that I miss the matrix of diagonal matrix of singular values. So what I can do to cheat, I just take this not as normed vectors, but with norms equal to the square roots of corresponding singular values. And here as well, not normed vectors, but the do you following me? I can be more, how to say, give more detailed. So I can hide this if I assume that these vectors are normed so that their norms are not unities, but the squares of the corresponding singular values of this matrix. So these matrices are simpler because they are orthogonal. These rows are orthogonal, these columns are orthogonal. It's a principal component analysis. And the very same formula is for k-means, except for these rows are centers of clusters, and these columns are binary vectors of belongingness. So each object, you have an object, shows belongingness to a cluster. It's either unity or zero. So you have k is the number of clusters here. These rows are the centers, and these columns are binary vectors, 0, 1 vectors of membership. And this model that you mentioned of fuzzy, when you put here not 0, 1, but fuzzy belongingness vectors, I developed this back in 1990 under the title ideal types. Because you see, when you have these vectors are belongingness, then it appears that the centers are convex combinations of objects. The centers are convex combinations of objects, and this means that they are not in the center, but they are on extremes of the points. And this idea was picked up with no credits by some Americans who developed a model of archetype analysis. You can find it. There is a, how to say, a set of works, archetype. Archetype analysis. You take Google Scholar, and you will find 1 or 2 papers every 5 years in this. It's when not only centers are convex combinations of objects, but also objects are convex combinations of centers. It's symmetric. I'm not sure how well this is developed. I don't watch it. But this is an interesting subject, and to my shame, I never thought of this as applying to fuzzy.
I think that I understood that one connection is because principal component, you find the first component and then the second one, which is orthogonal. And in his method, he
Very
finds
similar.
the first cluster
The
and
first
the second. And I think that one advantage, because you run just once, k-means you need to start many times. So you run
first, the second.
Yes, but just once.
Yes.
And then you don't need to repeat because you will find the same thing.
Because I'm doing these iterations for each of the clusters, but it can be done differently. There can be many different methods.
And one thing that I was thinking about this is that also once you find the K that you want, the rest are smaller clusters. So in the sense you are removing the least importance, like the least important principal components in that sense. So that's what I also thought, right? When you stop, then you kind of ignore the points that are less important in some sense.
I have no single criterion for stopping process. For instance, in that application to the analysis of tendencies, we found 7 clusters, but only first 3 were interpretable. So we pick up only 3 interpretable clusters, and we don't consider the rest. And still, it was published in the Information Sciences. So there is, unfortunately, I cannot develop one single criterion.
I understand. When you stop is that you run everything, and then you pick the first ones that are the most important. So in the same sense of k-means, right? You get all the principal components and you pick the most important ones to work with.
We tried it unsuccessfully. Maybe I should tell you one anecdote related to the entire story. Very important Americans, like from Stanford, once picked up this method. They probably heard of this and published a paper under the title Gene Shaving. Shaving, indeed, it's you shave. You shave the first cluster, then you shave the second. Unfortunately, they did not read my paper. They just only heard of the idea. So at each step, they changed the center. Each time they took here, I don't change the center, and they changed it to be a center of the second cluster. And I knew that it didn't work. So it was quite popular. And recently, I had a very big team of students from Pakistan. And they asked me something about my name or something. I said to them, look, I spent 5 years in the United States. During that time, I developed such a hatred of me, or maybe not acceptance of me among the United States people. So whatever I do, they don't refer to this, they change name. I suggested a method called B-clustering. They call it co-clustering. And I mentioned this shift, the gene shaving, and one of them immediately found some reference, and he read it. It is written that the method of gene shaving was invented by Boris Mirkin in that year. And I never looked at it anymore after this lecture they gave.
I forgot to say to you that Professor Mirkin was one of the first to work in big clustering. One of the first in the world, if I well remember. And he has many books about clustering. Okay.
But I have here the book. Just a second. I wanted to show
Yes, you can show us. No problem.
Where's the book?
Where's the book? Yeah. Core data analysis.
So this is my textbook. I first wrote it in 2011, and this is a second edition, much larger. And in second 11, I did not say core data analysis. I said core data analysis concepts, because I was afraid of the American criticizing me. So this is, now I removed the concepts. I also have a very recent book in Russian, a textbook in which I give an account of relation.
What is the title?
Here.
Yeah, but basic method for data analysis.
It's
Okay, basic method for data analysis. Okay, I see.
It's B. B is a Russian form of beta. This B. So we picked up the Russian alphabet was created by Greeks in 9th century, Greek monks, based on the Greek alphabet. And this is what we call Cyrillic. Cyrillic, because the name of one of these monks is Cyril. We say Kirill, we don't say Cyril, we say Kirill. Because we read this letter, well, doesn't matter what we do. Russia now is a kind of a minor country, not as big as it was.
Well, okay, I think that we can stop here. Thank you very much again, Professor Boris, to came here with us.